So now we have the software architecture and the low-level requirements. We can start driving the source code. And this includes, of course, the code written in the source language, for example, your program or your modules written in C. But it also includes the compiler instruction that you use to generate object code from the source code, and of course everything you need to link and load the data. Okay? So the executable object code is generated from the source code and the linking and loading data. Yeah. So remember this, source code includes all these things, not just the C modules that you've written. Now you can, of course, there's a variety of different languages out there. If you look at safety critical software, the primary languages used for safety critical software are really C, Ada, and assembly. And of course, there are some legacy products out there with some other languages like Fortran and Pascal. And of course, people have used C++, but it's been kind of limited, severely limited. Although now with the object-oriented design supplement, there may be a little bit more of an increase in C++, especially since a lot of the software engineering programs teach the students to program in C++. If you look at Java and C#, their use is mainly been for tool development efforts, in support, of course, development of safety critical software. And tools, something we're going to talk about in a later module as well. Okay, so how do you choose a language and compiler? Because the language and compiler itself, make sure that it's dependent on the readability of the code, the ability to detect errors at compile time, ability to support modularity, ability to support strong data typing, etc., etc. So there's a whole ton of reasons or a whole ton of capabilities that a language and a compiler have that you need to kind of consider in choosing that language or the compiler. Now, of course, it also depends a little bit on safety criticality. Some languages have been used more widely for safety critical application than others. So that also means that in the eyes of for example, the certification authorities, these software packages will be more attractive to use because they have already seen wide acceptance. Personal experience, if you have a team that's been a lot of experience with C, for example, this would give like C a preference state. So that's one thing. Okay, languages safety and tool support, very important. If tools are available or safety features are available, then that's a big plus for a language. Of course, the existence of interfaces with other languages may be a choice. The compiler track record, compatibility with selected target, and of course portability to other targets in case you want to look at the more long-term application where you may have to upgrade eventually to a different target platform. Okay, so let's look at some general programming recommendations. Of course, use good design techniques, no surprise there, and encourage good programming practices. This means, make sure to organize, if you do teamwork, organize your teams well, perform code walkthroughs, make sure to make use of good code examples, and of course adhere to that coding standard that you came up with. Also make the code available to the whole team so they can actually look what other people are doing and either use ideas from that or give some feedback to team members. Of course, make sure to reward good code and make sure that the team feels responsible for their product and give them opportunities for professional development. So in all cases, another recommendation would be to avoid software deterioration and also to keep maintainability in mind throughout your development. Make your code readable. On this slide I have a whole ton of things regarding the layout of the code or the code commentary. I'm not going to go through all those. Just go step through it. They make kind of sense. The textbook may have a little bit more text to each one of these items. So I would definitely make sure to read this chapter and include the code readability because for some of your projects you may have to write little pieces of code and I want your code to be pretty good looking or pretty decent looking here. Okay, so manage and minimize complexity. It's another recommendation. It means like make use of modularity to break the problem into smaller manageable pieces. This is very handy if you work in a team of people. You want to make sure that you reduce coupling between routines as much as possible. If it's not already being kind of enforced by the low-level requirements, you may want to address it a little bit too in your code. Make sure that if you use overloading of operators and variable names, that you be very cautious. Another one, use a single point of entry and exit for subroutines. In a sense, if you have a C subroutine, you can have multiple returns. So try to not do that. Have one point of entry, one point of exit. Keep the routine short and cohesive. In other words, if you look at a subroutine or a module, make sure that all the lines of code all have to do with the same kind of task. And make sure that you pick, of course, names for your variables that are logical and understandable. Also reduce the number of nested decisions, and of course as well as inheritance tree depth. It's like, you can be clever about routines and make it as a result hard to understand. Make sure that you try to make it simple and easy to understand. That's much more important. This way, if you do have a code walkthrough, other people can see what you're doing, rather than, hey, I came up with a clever one-line way of doing 10 lines of code. That's really not a good idea. So if you have nested if statements, you kind of want to rewrite that as if-then-else statements or case statements if can be. And if you work on your code, you can also always recommend to use a complexity measurement tool technique to identify complex code. And if it's too complex, you may have to do something about it and make it a little more simple. Now, it's always good to get kind of independent, like people are unfamiliar with the code, to review it. And of course, use modularity and information hiding to separate the low-level details from the module use. Yeah. So minimize use of interrupt-driven and multitask processes where possible. Of course, you cannot get around it in a lot of cases, but try to minimize it and make sure that you limit the size of the files. Okay, so to go back to the general programming recommendations, you may want to definitely consider defensive programming and make sure that your software is deterministic. So let's look at defensive programming. Defensive programming is really all the techniques that may be used to prevent the code from executing unintended and unpredictable operations by constraining the use of structures, constructs, and practices that have the potential to introduce failures in operation, errors in the code. Yeah. So you want to make sure that you do maybe you get input data errors by performing range checks, for example. You want to kind of avoid non-determinism. You don't want to have self-modifying code or dynamic memory or dynamic deallocation of memory. Things like dynamic binding, multiple inheritance. These things are not necessarily deterministic. So if they're non-deterministic, they're not recommended. So then it's defensive programming. So of course you want to avoid complexity, as I said on the previous slide, interface errors and logical errors. Oops. So you want to try and proactively address common errors, use assertions during development, implement error handling and exception handling, and a variety of other things that I have in this list, which is quite extensive, as I said. I would, in this case, I can go and talk a little bit on each of these items, but you really have to read the book here to get a little bit more insight into some of these bullets. Okay, now a couple of known troublemakers. Pointers. There's always some issues with pointers, so there's no way around pointers in some cases, but try to minimize it. Limit the use of inheritance and polymorphism if you use object-oriented programming. Again, I've said this a couple times, be careful with dynamic memory allocations. This is really kind of you introducing non-determinism here, so that means that something can be allocated without being under complete control. This is a problem. Minimize coupling, maximize cohesion. I think this is the third time I say that. Minimize use of global data. Use recursion cautiously or not at all, preferably. And avoid self-modifying code. So there's a couple of other things here that are things that I would avoid. Well, of course, as I said in the previous recommendation, you want to use assertions, for conditions that never occur. Error handling if conditions could occur. For example, if you have a particular range check, that a variable can only be in a certain range, then if it could potentially be outside that range, you have to check for it. And if it's outside the range, you make sure that you catch that off and get some kind of error handling for that. Okay. So exception handling, make sure that if something does break, a fault does happen, that that the program doesn't keep on doing stuff that is meaningless. Again, some more details over here. Okay, so if you look at the code, integration phase, this block diagram comes directly from figure 8.1. So you have the code phase, you generate source code, compiler instruction, link instructions. As I said, this is the code, the source code really. Then the source code and compiler instructions together can be used to compile the code, which may generate errors and warnings. You have to address these errors and warnings. And of course, if everything goes well, it generates object code. Then using the link instructions from your code phase, you link these together, and this generates executable code that you can then load on your target. Put maybe in the EEPROM of your processor or microcontroller or embedded processor. And of course, when it's confirmed loading, you get a load confirmation. Of course, make sure that if there's errors and warnings that you address those, because they may be indicators that something is wrong in either your source code or your compiled code. Okay, again, I don't know why I did this. Oh yeah, so you take the executable code, you load it on your target. This actual loading archive, there is some specific erring standards, erring 615-4 and A, we really talk about how this loading process takes place. Yeah, well, so loaded on the target, it's also for two things. Of course, for the end product, it needs to be loaded on the target hardware, but also during the test cases, in some test cases, where you perform hardware-software integration testing, you need to run it on the target hardware as well.